the Laplace Transform, the tool that takes the hardest equations in engineering and turns their calculus into algebra. In this video, we will not memorize it. We will build it from scratch. Every dynamic system an engineer will ever meet is a differential equation. A mass on a spring with a damper. A vehicle suspension hitting a pothole. A building in Kathmandu shaken by the ground beneath it. Different hardware, the same mathematics. Newton's second law gives us this. Mass times acceleration plus damping times velocity plus stiffness times displacement equals the applied force. And there is the problem. Acceleration is a second derivative. Velocity is a first derivative. This equation mixes a function with its own rates of change, and that is exactly what makes it hard. So here's the wish. What if we could trade every derivative for a multiplication? Trade the calculus for algebra? That trade exists. To find it, we first need one special function. Every differential equations mix a function with its own derivatives. So ask, is there a function whose derivative has exactly the same shape as the function itself? A polynomial? No. Differentiate t squared and you get 2t, a completely different curve. The exponential? Yes. Differentiate e to the st, and you get back e to the st, just scale by the constant s. Same shape. Same curve. Only the size changes. Write that down because the entire Laplace transform stands on this one line. The derivative of e to the st is s times e to the st. Differentiation does not change this function. It only multiplies it by s. In other words, for this family of functions, and only this family, calculus already is algebra. Differentiation is just multiplication by s. One more move. Let us be a complex number, a real part sigma and an imaginary part omega. That single letter now hides an entire family of behaviors, and we should go meet them. This is the S-plane. Every point on it is one value of S, one member of the exponential family. Real part sigma sideways. Imaginary part omega upward. On the left half of the plane, sigma is negative. Every signal here decays away. These are the stable behaviors. On the right half, sigma is positive. Everything here grows without bound. Instability lives on the right. And moving vertically changes omega, the speed of oscillation. On the imaginary axis itself, signals neither grow nor decay. They oscillate forever. Keep this map in your head. When engineers say a system is stable, they mean exactly this. All of its exponential atoms live in the left half of the S-plane. Here is the plan. Take any signal f of t. We want a machine that answers one question. How much of each exponential atom is hiding inside this signal? Take the simplest interesting signal. F of t equals e to the minus t. Upward decay. Secretly, it is a single atom. The atom at s equals -1. Pretend we do not know that, and let the machine find it. The machine works like this. Multiply the signal by a probe, e to the minus sigma t. Then integrate. Add up the area under the product, from time 0 to infinity. That area is one single number for each value of sigma. Watch the readout as we sweep the probe. Sigma large. The probe decays fast, it crushes the product, and the area is small. The probe and the signal have little in common. Now sweep sigma downward. The probe decays more slowly. The product fattens, and the area grows. Keep going. Let sigma go negative. The probe now grows, pushing against the signal's decay. The area climbs faster and faster. And right at sigma equals -1, the probe exactly cancels the signal. The product becomes a constant. Its area is infinite. The machine is screaming. This is the atom hiding inside F. That machine, multiply by the probe, integrate, read one number per S, has a name. This is the Laplace transform. F of s equals the integral from 0 to infinity of f of t times e to the minus st dt. The signal times the probe integrated. Nothing more. Let us run it on our decay, e to the minus at. Every step, no shortcuts. Substitute the signal into the definition. The two exponentials merge, e to the minus s plus a t. Integrate. The antiderivative of an exponential is itself divided by its own rate. At the upper limit, the exponential dies to 0, provided the real part of s is bigger than minus a, exactly the condition our sweep discovered. At the lower limit, it equals 1 over s plus a. The transform of a pure decay is the simplest fraction in mathematics. And look where this fraction blows up, at s equals minus a, exactly where a sweeping probe blew up. That special point has a name, a pole, and it is the atom's home address. Here, plot the size of f of s along the real axis, and you see the signature, a sharp spike at s equals minus 1. Engineers mark a pole with a cross, and this generalizes into a dictionary. A decay puts one pole on the negative real axis. A pure oscillation puts a pair of poles on the imaginary axis, at plus and minus j omega. A decaying oscillation, the ring down of a structure, puts the pair in the left half plane. Real part, how fast it dies. Imaginary part, how fast it rings. So a transform is not a formula to fear. It is a map. Find the poles of f of s, and you have found every exponential atom that builds f of t. Plot this. Now for the payoff. What does the transform do to a derivative? We will not quote the rule, we will earn it. Start from the definition. The derivative of f times the probe, integrated. Integrate by parts. Differentiate the probe. Integrate f dot back to f. Two pieces appear, a boundary term and a new integral. The boundary term. At infinity, the probe kills f, leaving 0. At time 0, it leaves minus f of 0. The initial condition walks into the algebra by itself. And the new integral is just s times the transform of f. There it is. The transform of a derivative is s times f of s minus the initial condition. Differentiation in time has become multiplication in s. Apply the same rule to the derivative of the derivative, and the second derivative falls out. S squared f of s minus s times f of 0 minus f dot of 0. No new work. The rule simply feeds itself. That is the whole trade. Every dot becomes a power of s, and the initial conditions come along for free. A differential equation is about to become a fraction. Now, time to use it. A damped system released from rest. 1 unit from equilibrium x double dot plus 3x dot plus 2x equals 0. X of 0 is 1. X dot of 0 is 0. Step 1. Transform every term with the rules we just proved. Each derivative becomes a power of s, and both initial conditions drop straight into the equation. Collect the x terms. The calculus is gone. This is pure algebra. Step 2. Solve for x, 1 division, and factor the denominator. 2 poles, s equals minus 1 and s equals minus 2. Before we go further, the map has already told us the answer's ingredients, 2 decaying atoms. Step 3. Split the fraction into one simple piece per pole using the cover-up method. Cover s plus 1. Set s to minus 1. A equals 2. Cover s plus 2. Set s to minus 2. B equals minus 1. Step 4. Invert, using the only pair we need. 1 over s plus it comes from e to the minus at. The answer x of t equals 2e to the minus t minus e to the minus 2t. Never skip the check. At time 0, 2 minus 1 is 1, correct. Differentiate. Minus 2 plus 2 is 0, correct. Both initial conditions are satisfied. And here is the motion. Released from 1, it slides home without a single oscillation, because both poles are real and negative. The picture was already written in the S-plane. Time to step back and see the whole machine. 2 worlds. In the time domain, the problem is calculus, and it is hard. Cross the bridge with the transform, and the same problem is algebra. Solve it, and cross back with the inverse. And this small table is 90% of daily engineering use. A constant, a decay, a sign, and the derivative rule. Everything we use today, and everything you now know how to derive yourself. Where the ground shakes and machines vibrate, engineers do not fear differential equations. They read their poles. Next time, the transfer function, where these poles decide whether a design rings, settles, or shakes itself apart. See you there. Step back and